Okay, well, good afternoon, everyone. It is 2:02. To be respectful and cautious of everyone's time, we will get started. As I noted, the voice you're hearing right now is Josh Kramer. I'm the Director of Educational Workforce over at NCDM and America Makes, and I will be your host today for this America Makes TRX web series. And so I will provide a little bit of background on our TRX series as well. And so we created this platform called the America Makes Technical Review and Exchange Webinar Series so that we really can convene the additive manufacturing community on a monthly basis. And so by doing this, we're supporting not only our mission at America Makes to expand and accelerate the footprint of additive manufacturing inside the United States. And so a couple different notes that I hope everyone can amend to, and we'll kind of keep the line clear and make sure everyone can hear. We kind of eliminate some background noise. We will be using, there is a question and answer, a Q&A box inside the webinar, and we would ask that you type your questions there. Dr. Liu, that's joining us today, and will be our presenter. We will have a Q&A session at the end of his share and his presentation. And so again, please use the question and answer box. We have myself as well as Dr. Liu that's able to see that, and we will be monitoring the Q&A. We can actually reread your question for you. That'll eliminate us kind of jumping on each other as we try to get those questions answered just the same. And so again, please feel free to type those in. And again, if you're not already on mute, everyone should have been muted as they came in, but to keep the line as clear as we can, being a large webinar, let's make sure everyone is muted. And then Dr. Liu, if you can switch to the next slide for me.
Oh, I thought I'm trying to go to the next slide. I don't know why it doesn't go. That's interesting.
And so while he is troubleshooting that a little bit, please allow me to introduce Dr. Liu. And so today's webinar will be presented by Dr. Ming Liu. Dr. Liu is the Keith and Pat Bailey Distinguished Professor in the Department of Mechanical and Aerospace Engineering at the Missouri University of Science and Technology, where he is also the Director of Intelligent Systems Center. And so he founded the Missouri S&T Center for Aerospace Manufacturing Technologies in 2004 and served as the director there until 2016. During our time today, Dr. Liu will provide us with an introduction of additive manufacturing technologies, as long as applications in aerospace, healthcare, electronics, and other industries. Dr. Liu will also provide us with an overview on recent advances in additive manufacturing equipment technologies, as well as Dr. Liu will also wrap up the session specific to the TRX web series with research and innovation opportunities in the future of advanced manufacturing. And so I had the pleasure of kind of previewing a little of this material yesterday. I think this will resonate with everyone that's joined us today. There's a lot of great information, a lot of great research, and a lot of great work that he and the team over at Missouri S&T have done and put together for us today. And so with that, I would like to pass it over to Dr. Liu, and who is our presenter today.
Okay, Josh, thank you very much. Good afternoon, everybody. I'm delighted and feel honored to give a presentation today on recent advances and future opportunities in additive manufacturing. And I know that the audience, some of them may not have much knowledge, others are experts already. So I'm going to assume some of you may not have the knowledge. I'm going to start from the very beginning, talking about what additive manufacturing is, and then get into applications, research, future opportunities. So this is the public images of 3D printing. In academia, it's usually called additive manufacturing, but the 3D printing is more popular in the news medias, TV channels, magazines, and so forth. But this is 3D printing, or additive manufacturing is perceived to be new manufacturing technology which could just make anything that you like to make. You can make batteries, you can make architectural models, guitars, guns, jewelry, ornaments, you name it, or even artificial heart, but that is actually many years away. So for additive manufacturing, we always start from CAD model of a three-dimensional object, from which we could, all the CAD systems can generate so-called STO file, which is a triangular meshes approximating the surface boundary of the three-dimensional object, from which we could generate slices, which has inner contours, outer contours, and which the software can be used to generate the trajectories for the tools to follow. When I say tool, it could be laser beam, it could be a nozzle for inkjet printing or for extrusion. And you then fabricate the parts layer by layer until it is completed. And afterwards, you may have to go through support material removal, binder burnout sintering, or polishing. There is a standard definition by ASTM International Committee F42 saying that additive manufacturing is the process of joining materials to make objects from three-dimensional model data, usually layer by layer, as opposed to subtractive manufacturing methodologies. And they categorize this technology into 7 categories, as shown here: wet, photopolymerization, material extrusion, powder bed fusion, material jetting, binder jetting, sheet lamination, directed energy deposition. And I have a slide to summarize and illustrate each of these processes. So wet photopolymerization, a popular name is SLA, or laser stereolithography, where the laser is directed to cure photocurable monomer liquid resin in the vat according to the cross-section of a CAD model. After that, you put another layer of this record resin, and then you do another layer and so forth until the part is completed. The material extrusion, well-known name is fused deposition modeling, where the material, usually thermoplastics in the filament winding, is melted by the head and then put in some pressure to extrude out, just like extrusion of toothpaste, layer by layer. In the case that we are trying to extrude ceramics, that would be difficult to put into filament winding unless the viscosity is very low. In that case, we could just make paste directly, which could be organic or aqueous paste. The powder bed fusion is a very popular process where the powder is in a bed, and they use a laser. It could be CO2 laser, it could be ND-YAG laser, could be even E-beam to melt the layer according to the cross-sectional geometry. And every lot, you put another layer of powder, and then you have the roller spreader to flatten the surface and add another layer. And depending on this, whether it's based on laser or E-beam, the process could be selected laser sintering, usually for thermoplastics, or selected laser melting for metals. Material jetting, or like polyjet printing, is easiest to understand. It's just like our inkjet printers for printing a piece of paper with the text and graphics, but except that's one layer, then you are doing layer by layer, and that material could include the part material, could also support material, but of course at the end, the support material would have to be removed. In binder jetting, the material to be jetted is not the material of the part, but the binder. So we have powder material in the powder bed, and the binder is jetted to bind the particles in the powder together according to cross-sectional geometry, and then you build the part, and often it's called green part. You may have to infiltrate with some of the materials to have a strength, or sintering the part after it's built Machine lamination is often called a laminated object manufacturing. And in early days, you basically have a paper, and you cut the paper. You have the paper use a CO2 laser to cut according to the inner and outer contours, and you also cut the rest of the paper so that you can take the part out after it has been built. And after your layer has been built, you bond to the previous layer, and you just keep going. And lastly, directed energy deposition, sometimes called lens or laser engineered net shaping, because it was initially developed by Sandia National Laboratory. And in this process, you have laser directed to melt powder, or sometimes could be rod, which is provided through the nozzle, or you just supply the rod, and you melt that, and you solidify, and you go to the next layer. So these are the 7 categories of additive manufacturing processes, and I have video clips to show them. So these are the video clips for these 7 processes: binder jetting, wet photopolymerization, material jetting, material extrusion, powder bed fusion, direct energy deposition, and machine lamination. Okay, so why AM? Why additive manufacturing? What are the unique advantages of this manufacturing process? What are some of the representative applications? I will go through this in the next few slides. So the main advantages of AM are, one is we could have geometric complexity. We can make geometrically very complex parts at no additional cost, unlike conventional processes. Second, material complexity. You could have multiple materials or gradient materials built in the same part. 3, structural complexity. You could have a ladder structure of various architecture. You could remove some materials not affecting the performance through topology optimization. And because of the nature of the process, you add material bit by bit, layer by layer, and you can make very complex geometry. This is really good for personalization and individualization, such as the healthcare industry, for making medical devices, implants, dental prostheses, and also good for power repair. And finally, you could make integrated active systems, including the structure, components, the sensors, and actuators, without having going through the assembly process. So I'm going to give you the representative applications taking advantage of these AM advantages. Okay, so these are some of these aerospace applications. You can see that a more recent one, well-known one, is Boeing 787. Uses the titanium parts by additive manufacturing, which is FAA certified. And for each of those parts, the estimate could save about $2 million. Also, if we have a turbine blade, titanium turbine blade, which is very expensive, and then if a blade is broken or worn out, you don't want to just throw away. So you could use additive manufacturing. In this case, is a lens process, direct energy deposition to repair the part, and with a very strong excellent properties, just like original one. A famous example is the fuel nozzle for LEAP engine by General Electric, as shown on the bottom left. And this used to be more than 20 components, and they have to be joined together into this fuel nozzle, but with additive manufacturing, they can make all these in one piece. Another example is a fuel heater for ATP engine, also by General Electric. Another example is the thruster for SpaceX Dragon capsule. In terms of automotive applications, this shows some of the examples. As you can see that this can be used for car chassis, could be used for some front structure for media storage and crash optimization with internal cooling channels. And all those parts, if not by additive manufacturing, they will need to make into many components and then join together. Also, with additive manufacturing, we could have conformal fuel passage, as shown here, the 3D printed pump by Delphi. In the conventional process, you have to use the drill to drill the holes for this fuel passage, which is not as good as the use of additive manufacturing. And also, we could have all kinds of lattice structures to increase shock energy absorption in crash. So those are metal parts. How about thermoplastic components and ceramic components? So this one shows some polymeric parts by AM, including Invisalign clear aligner for orthodontics, very famous. Also, Envision Tech hearing aid, which is put into the ear. Everybody has a different shape, different geometry, so this is very good for personalization. We have some parts here, like gears made by HP's multi-jet fusion technology. You can have different materials, different colors, very sophisticated geometry and assembly. This car, the Cobra, in this case shown here is 26% in weight, is made by additive manufacturing. Actually, this was demonstrated by Oak Ridge National Laboratories. They were able to do this from the concept of wanting to do additive manufacturing, plus doing that, and plus the polishing, painting, everything together, all in 6 weeks. And finally, at the bottom, we have this shoe. The shoe sole, which is made by additive manufacturing with a lattice structure by a carbon machine. And as you can see, it takes advantages of additive manufacturing to be able to make these lattice structures in all kinds of different designs, and with some good functions, like you can put on the proper pressure and some certain part of free. So this is the good advantages of additive manufacturing. Ceramic parts by AM. You can see that here we show some coffee mugs, some design coffee mugs, ceramic ornaments of various kinds. Could also glass, amorphous ceramics, right? Different kinds of glass, so for ornaments. And often ceramics are kind of difficult to be shapen, And so one way to do it is that we print a polymer. And from the polymer, because polymer you can change the shape more easily, and then from the polymer you derive ceramic components, including lattice structures, and which can be done after pyrolysis of polymers. Okay, so those are single materials of a complex structure, but also we could also use additive manufacturing for 3D printing of multiple and graded materials. I can see here that we can integrate additive manufacturing with direct writing to make structure components with electronics, and we could even have a conformal printing according to the shape of the structural components and put it on the surface. We could even have more than just the multiple materials, but the materials can be graded, can be mixed together and doing some grading. As you can see that here we have some helmets some boots, eyeglasses, and by the use of multiple materials, we can change the colors, we can change the properties. Some portion you like to be hard, some portion you like to be soft, and you have all these choices. And the gradient materials allows you to design not only geometric correctly, but also have the desired properties as well as the colors. Okay, this one shows a study of a European project, and they want to see the impact of additive manufacturing on the environment to reduce CO2 emission. And so this particular example, they have the swivel arm for a TV screen on an aircraft. And conventional, this is done by machining, and they want to compare that with selective laser melting of a lattice structure, as well as selective laser melting of optimal geometry through topology optimization. And so they want to look at life cycle impact of CO2 emission, and so that you have to look into CO2 emission due to raw materials, due to the manufacture of the components, due to the distribution of the products, and also finally the usage. And in this case, because this is used for aerospace in the aircraft, and the usage, the CO2 emission dominates all the rest. And so you can see that by the use of additive manufacturing, it can reduce CO2 emission by more than 50%. Okay, there's the applications in healthcare industries. There's this additive manufacturing is perfect for healthcare industries because everybody has sort of different shapes in terms of their needs and their body, their skills, and all that sort of things. So we could use additive manufacture to make a hip implant, knee implant, a skull implant, and also for orthosis, for protection devices for the legs, for the hands, for the arms. And finally, we could use additive manufacturing to fabricate integrated structures and sensors and actuators and batteries all together without having to go through assembly, and end up with robots, for example, for the land, for the sea, and for the air. All these are possible through additive manufacturing. I want to next talk about some of the recent advances in additive manufacturing, and this is mainly I will be talking about the work done at Missouri University of Science and Technology by myself and also my colleagues. We are very strong in additive manufacturing research with, as you can see here, about 15 faculty members doing various kinds of additive manufacturing research. We have a long history starting from 1995. I started working on something called rapid freeze prototyping of water. Basically, we freeze water droplets to form ice sculptures, which can be used as patterns in investment casting in lieu of wax patterns. My colleagues, Dr. Frank Lu, was working on direct energy to position for making parts, as well as integrated with CNC machine, so that you have hybrid additive subtractive manufacturing. And then we're working on lots of different things, ceramic additive manufacturing with organic paste, with aqueous paste, which could be in sub-freezing temperature or room temperature. We use selected laser sintering for making ceramics, and we develop additive manufacturing for glass. And we do direct energy deposition for weighted metals. We look at fused deposition modeling of high-performance thermoplastics. We develop a new process called laser foil printing. We look at optimization of selected laser melting, and also look into electronics, additive manufacturing, battery additive manufacturing, and also additive manufacturing in the micro and nano scale. So below, I'm going to highlight a few different processes that we have been working on. So this process we call ceramic on demand extrusion process, and you can see that we have the schematics, we have the equipment, we have the parts made by this process, turbine impeller, gears, blower housing, thin wall parts, and the part is made in a little tank, and every layer after it's built, this is not immersed into the liquid, but after the layer is built, the liquid is then added to flush with the surface to prevent an even evaporation of water from the side. And then the drying is done by radiation heating from the top. And so this is to prevent warping and cracking. And we have shown that we are able to make parts from alumina and zirconium up to relative density of 99%, which is very good. Very nice fracture strength. And also the materials can be mixed together to make functional graded materials. My colleagues at Kinzo was working on glass additive manufacturing, used a laser to melt the glass rod. In fact, he could use more than just one glass rod, and they could have different refractive index, and you can provide the sort of different feeding rate and to have a different compositions. Therefore, you can make transparent glass of this varying refractive index, in addition to making glass artifacts of different geometries sort of for ornaments. And this is the main challenge of this one here is that the processing temperature is higher than polymers, and the viscosity. The viscosity is high, which is good and bad. Good in that allows you to make a free-standing structure, but difficult for bubble to evacuate, and also glass is much more brittle. And this one shows directed energy to position of functional gradient materials. This is done by my colleague Frank Liu. And in this process, the main thing is that we want to do the gradient materials because they have different properties. Some may be stronger, some other materials may be lighter, or could be more corrosion resistant, web resistant. So we want to be able to ability to vary material from one to the other. But if we just change from one material to the other material, the thermal expansion may be so different, and they tend to be cracking. And so you want to have gradient materials. You want to change gradually. So in this case, we change the gradient. The material composition from pure titanium to gamma titanium aluminide. And you can see that so we have a region from 1 to 6, and with a change the composition between the two materials from about 100% one material to 100% the other material, but then going through the gradient change of the composition, and you can see that the microstructures are different, and the composition of in terms of the titanium content, aluminum content, they are different, and the hardness also different. And this is very important. This allows us to have a lot of flexibility to build parts with not just a single material. And also we developed a process called laser foil printing, which is essentially sort of layered the process where you are laminate, right? So like a laminate manufacturer, you laminate from one metal foil to another, but you cannot simply just kind of laminate that because it's difficult to bond them together. So what we do is that we do spot welding, and then continuous laser to do pattern welding. So you weld the top layer to the bottom layer, but then you go through the cutting process using the pulse laser so that you can cut every cross-sectional, you have the right contour. And we have shown that this process, because of the use of the foil instead of a powder or rod, the thermal conductivity is higher, and therefore cooling rate is higher, and therefore the strength of the part made is higher. And also because of the high cooling rate, this is good not only for making crystalline metals, but also for amorphous metals or metallic glasses. And so here we show that we are able to make parts from metallic glasses. And sometimes it's difficult to, because of compatibility issues, you may have to have some intermediate metals so that including the metallic glass. So all these are part of research. We also have counted. This is Hempen is working on 3D printing of lithium-ion battery, and so you can see that he used this aerosol, this fine jets to make the parts, and it could be different materials. As you know that in battery you have the materials. You need to have active materials. You need to have electrodes. You need to have current correctors, and so with additive manufacturing we can have all these different materials made by a single machine, including all these materials and plus even battery enclosure. And with the use of additive manufacturing, we can print complex shaped batteries for increased power density interspace constraints. Another research by Dr. Hempen is very interesting, is micro-nano 3D printing by femtosecond laser. So here we are not talking about this macro or meso scale, but micro and nano scale. And the way you can see that he is making some gold pillar array, and the width is less than 1 micron. And the way this is done is by excitation of nanoparticles using femtosecond laser in making the 3D micro nanostructures. And this one provides a lot of flexibility because of the process. We all know this two-photon lithography for making micro nanostructures in polymers, but this one, with this process, we can make them in metals, in ceramics, and semiconductors. One example applications is high power density micro battery. Okay, so next I want to talk about some future opportunities in research and innovation. So there was a lot of research to be done. One of them is to have engineer material properties, not by changing chemical compositions, but by structures. All right. So we can have exactly the same materials, but we could change the material properties through the design of lattice structures. And we know that here that if a metal tends to be stronger, but density is higher than polymer and all that. But the main thing is that with the lattice structures, no matter what the materials is, there are different kinds of lattice structure. There is a benzene-dominated lattice structures, which is like in the form, which is good for absorbing energy. But if you want to have a strength, you want to have a stretch-dominated lattice structure, shown there. And also, if you want to have some exact properties such as negative Poisson's ratio, which is often called an auxetic structure, you could also do that. And that's possible because of the design of lattice structure. Not only in meso and macro scale, but also in micro and nano scale. And we could have different lattice structures, which could be periodic, could be aperiodic, and the material could be polymer, could be metal, could be ceramic. And we can design all these and fabricate these micro nano scale lattice structures to generate high strength and modulus. So very high strength to weight ratio. Another way of generating new properties is not by this lattice structure, but by material. We could have gradient materials, as I mentioned. So some materials may be strong, other materials may be hard, corrosion resistant, wear resistant. So depending on applications, for example, if you have this, the two surfaces in contact, you may want to have the material to be wear resistant, but on the other portion of this part, you want to be able to strong and be able to be tough and absorbing energy. Therefore, you want to build the parts with gradient materials, with multiple materials, but because the possibility of warping and cracks, you want to have gradient materials. But the difficulty of having graded metals or ceramics is that they may have a different coefficient of thermal expansion, so it's easy to get warping and cracking. And also the ceramics may have different sintering temperatures. Metals could have different melting temperatures, and they could form intermetallics. So these have to be taken into consideration in the design of gradient materials to make sure the materials are compatible, or maybe you need to have some intermediate materials in between to make it work. The modeling simulation is always very important. People have been doing a lot of modeling simulation, but in the future research, we need to look into not only the process modeling simulation by looking at the melt pool. So right now, most people are looking at, let's say in this case of selected laser melting, they are looking into thermal modeling and simulation to predict microstructure and mechanical properties. But they have not looked into the upstream, right? So what do we mean by upstream? Well, what is the powder bed density, and how is that affected by the various material and the process parameters? And they are also important. So in the future, we could look into, for example, including in the modeling simulation, the discrete element method simulation to predict powder bed density as a function of the powder morphology, the powder chemistry, recorder geometry, and so forth. And with that predicted powder density as input to the thermal modeling and simulation, and which then predict the melt pool geometry and microstructure, mechanical properties, which of course have to be experimental measured. And this contributes to in-process part certification. And in order to have a good model, we need to have good understanding of the physics. So advanced instrumentation and the measurement are important. And this one shows work done by my colleague, Liang Chen, in collaboration with Argonne National Laboratory. So they have the equipment, the facility to do in situ X-ray imaging and diffraction. So he basically is looking for when the powder is melting, what's the dynamics of the powder particles spattering. And so you can see that there are particles there, and then when it is heated up, it's going to spatter. And so this X-ray imaging allows you to observe that, and that information then can be incorporated into a mathematical model. Another one is to look at the melt pool to have a better understanding of the melt pool dynamics, the powder melting and solidification. And this is extremely important for modeling simulation of the melt pool, temperature, and also geometry. Additionally, we need to look into advanced process monitoring and control, because currently most of additive manufacturing processes are open loop control. Right? They tune the best process parameters to make the best part, And the way they are doing, which we call power-to-part control, is that you provide some input, like powder, morphology, chemistry, laser power, hedge spacing, and so forth, and you use that set of parameters to build the part, and you change the values of those set of parameters, and you build some other parts. At the end, you try to find out which set of parameters is the best. You try to find the optimal set of parameters in building the best parts. Of course, in the process, you also look into these thermal modeling, thermal history, microstructure, engineering properties. The problem is that there's a lot of uncertainties. When you said, well, the powder, right? The powder morphology and chemistry, every batch of powder is different. And also, there's a lot of uncertainties in terms of the process parameters. The environment may change. The humidity, temperature of the environment may change. So with so many parameters out there, in order to assure the quality of the manufactured parts, we need to do feedback control. Could be point-to-point control or layer-to-layer control during the fabrication process. And with that, for doing this feedback control, we also need to have mathematical models. But these mathematical models are very different from the advanced modeling simulation, which you want to have very sophisticated models to do the best prediction. But for feedback control, actually you want to have a simplified model. Otherwise, you cannot do real-time control. So we want to reduce complex mathematical models to lower models for real-time feedback control. And in-process part certification is very important because in additive manufacturing, unlike conventional processes, there tend to be more variations. So you cannot simply just make a whole bunch of parts and just select a few and test those, and then you're done. But you almost have to certify every single part. But if you want to certify every single part at the end of fabrication, will be very time-consuming and costly. So what is very desirable is part certification during in fabrication process, not after part manufacture. In order to do that, we must have accurate in-process sensing and prediction of parts, dimensions, and properties, and rapid and affordable metrology for in-process measurement. And then process innovation is very important. Companies care about that. You want to make parts faster and larger parts and cheaper. So those are three things: bigger, faster, and cheaper. As you can see, there are several machines here. He has this binder jet based additive manufacturing machine. They said can print 10 times faster than current machines. They also claim they have selected laser melting machine, which is the largest in the world at the time. And HP has a multi-jet fusion printer. They said it's 10 times faster and 50% cheaper than other 3D printers for similar purposes. And this big area additive manufacturing of band machine by Cincinnati Micron in collaboration with the Oak Ridge National Laboratories. In fact, this is the machine which makes the cardboard sports car animation. And they are able to make the large parts very quickly. And more importantly, is using commodity thermal plastics, therefore reduce cost drastically. And in process innovation, I think the most challenging one is 3D printing, 3D bioprinting. In 3D bioprinting, we are trying to use the 3D bioprinting to make scaffolds, tissue models, and eventual organs. But this has a lot of complication and difficulty because we are talking about making lots of components, including, for example, for the organs, the artery and vein, and capillary networks, and lots of different materials. And all these are very fine resolution in terms of dimensions. So be able to have novel bioprinting to fabricate complex external and internal geometry to fulfill biological, biophysical, biochemical, transport, and anatomical requirements. This is very challenging. And there are people doing some research on that. You can see here there are people making artificial ear, some cartilage, tissue on a chip, and making hydrogels with internal channels which can be perfused with cells by the use of digital micrometer. These are just some of the examples, but this is just a start. Besides the process innovation, another one which is important is in 3D bioprinting is material innovation, right? Because you need to always have the process and materials. And so here we need to create tissue models or even organs, functional organs, by novel biomaterials and growth factors, as well as multiple cell types. And so there's a lot of innovation to be done. Like today, so people are trying to make these artificial organs. So to make organs is that they do this the cellularized approach. They take these organs from humans and animals, and then they take the cells out, and they use the materials, and they put into some new cells in there. But in the future, what will be desirable is not that, is bioprinting of an anatomically accurate embryonic organs. So you don't use those cellularized material, but you just take some synthetic materials, you put some embryonic cells in there and try to make the organs. But of course, that is more into the future, but in the more immediate use is to making tissue models, right? But in that case, it's still material is very important because we like to use the synthetic material, which will provide the same characteristics as human tissue, like human liver tissue as shown here. And when it does this toxicology screening, it has some certain characteristics. And what we like to do is that with synthetic materials, when we do the screening, we have the same characteristics. So what materials are the proper ones to use? These are critical. Finally, is 4D printing. So 4D printing is 3D printing of programmable materials to create structures and objects that can change the shape in response to change environments such as the temperature and pressure and the humidity, magnetic field, and so forth. As you can see here, some examples here. You can have this structure, 2D structure, right? And you can program that by putting some heat, and depending on your programmed heat, you can then change to different shapes, different 3D shapes, right? And it's kind of nice to do that because trying to make those 3D shapes may be difficult. Another example is the use of hydrogels, and you put that into the liquid, and you start with the 2D shapes, and then you gradually change to 3D. And so this has the properties of shape memory, except this is geometrically it's much more complex. So in summary, I have given a brief overview of additive manufacturing processes. I talked about the unique advantages of additive manufacturing, the representative applications in the various industries, aerospace, automobile, electronics, healthcare, and so forth. And I presented some recent advances in additive manufacturing technology due to research at Missouri University of Science and Technology. And finally, some future AM research and innovation opportunities are envisioned. Thank you very much. Any questions?
If folks have questions, please feel free to add them to the Q&A chat box. I will start us off. I don't see any questions in there just yet. But one question, Dr. Liu, that I would ask that probably a lot of folks on the phone would enjoy is maybe if you could talk about a couple case studies through the research that you all have done at Missouri S&T using additive technologies and processes. Is there a case study that you can walk us through of a part that was, obviously more efficient or designed to be printed versus a traditional part?
Okay. We tend to do this not so much in case studies. We tend to do kind of more of basic research and the property. So when you ask the questions, I have to think a little bit about. Okay, now I can think of it. All right. So we did a project with a company, and the project is to to make the molds for composite manufacturing. Okay. And so in the molds for composite manufacturing, traditionally would be done by machining of metals such as aluminum. And so the project was trying to replace that by using additive manufacturing of course, you can also use additive manufacturing of metals as well. But the thing is that in the project, when I was doing the study, and actually, by the way, that project is also funded by American Makes, right? So sort of different aspects of the project. And so the project was trying to use, because they are some years ago they have this auto material, and auto material has a lot of properties that are very similar to aluminum in terms of the strength and the modulus and all that. So we are trying to use this atom, and then have the mold made by field deposition modeling, stratasys machine, and not only to have the mold made by that, but also to see if, because of additive manufacturing. So we were trying to see that it's possible to make the mold, which could have some materials removed. So that's so-called sparse build. Right? So instead of solid build, instead of trying to in some applications you want to have this full density, close to 100% density. And in that case, we said, well, okay, fine. Let's try to build this mold with 100% density, but also let's try to build the mold with 80% density and 60% density, and trying to find out what the properties are. If you have some load in, what the deformation will be, and whether deformation is acceptable or not. Right? And so looking into the savings by removing materials because of additive manufacturing, and also looking at the strength to weight ratio and all these parameters. Okay, as well as the the various geometric factors such as the wall thickness and those parameters to see the effect of those. So that's kind of on the top of my head that I can think of.
Okay, great, and thank you. And so we have a question coming in from Dan, and Dan had asked if you are aware of any research in the characterization of design of the thermal properties of additive manufactured parts.
Oh, let me see. I'm reading the question. Are you aware of any research in the? Say it again.
Yeah. So he asked, are you aware of any research in the characterization or design of thermal properties of additive manufactured parts?
Oh, I'm pretty sure there are lots of research done on this. Maybe too much to name. We are looking into it ourselves, and I'm pretty sure there are many places which they are looking into the thermal properties of additive manufactured parts. For example, we are looking at the parts made by additive manufacturing, and looking at how they perform at the different temperatures, especially elevated temperatures. to see how that is going to affect their strength, modulus, the various properties. And of course, for us, we are looking at one specific materials. Other people will be looking at the other materials. And they make this by, because there are so many different processes. And I'm pretty sure that they are of great interest by many people, especially the industry. They want to apply the parts, and they are depending on the environment. They may have to use the parts in a high temperature environment.
Yeah, and so Dan followed that up, and he's looking specifically in the context of heat transfer, looking at things like thermal conductivity, specific heat, et cetera.
I don't know if I've come across many papers like that, okay. But if you ask me one specific one, I'm not quite sure what I might be sort of. I don't have any one which is stick out from my head, but I'm pretty sure that you can search the internet and find out lots of papers on that.
Okay, thank you. And so it's 2:58. We have 2 minutes left. If we have some other questions, feel free to share those, and I'll throw another one out. And so you had mentioned 4D opportunities in additive as well. How far in the future do you feel 4D may be?
How far into the future? Oh, they are. I think that we are just kind of in the beginning of 4D. Now, the 4D is the concept. The concept has been around for some years, but in terms of research, because in the 4D you got to look into the external stimuli. You got to say, well, okay, fine. You want to change the shape. Like just the one example I give you there. So if you want to change to sort of the desired shape, and you got to say, well, what the original shape should be before you change the environment, right? And when you feel that, it could be sort of a 2D, and how should you be doing that? And then after that, when you want to change shape, depending on how shape you want to change, and how should you apply the heat and change the environmental factors. So there are lots of things there which needs to be done.
Okay, great. All right. Well, right at just about 3 o'clock, Dr. Liu, first and foremost, we all want to thank you. And I can speak from our American Makes team. Thank you for your presentation today, and obviously I could probably speak for all of the attendees on the phone. I myself enjoyed the presentation and your knowledge and sharing your knowledge with all of us for a little bit today. And as far as follow-up, Dr. Liu, your contact information was up here a minute ago, but feel free to reach out. Also, the opportunity to reach out to Tiffany Westbay, who heads up membership and actually manages our TRX webinars for us at American Makes. If you're interested in hosting one, interested to learn more about the work that we do or membership and those kind of things, obviously, having access to the research, some of this research that we discussed today and some of the great work here, feel free to reach out to us and join some of the great work that we have. So with that, Dr. Liu, thank you. Thanks for all our attendees for joining today, and we look forward to seeing you join us again for another American Makes TRX webinar.
Thank you very much, and Josh, as well as everybody else. All right.
Okay. Have a great day, everyone.
Bye.